Hi, I'm Tomsey, and I'll be presenting the paper IQ, Incremental Learning for Solving Qsat. In this paper, we present a new Qsat solver, IQ, which uses good strategies to help solve Qsat problems. By doing so, it achieves state-of-the-art performance. What is Qsat? Qsat is a satisfaction problem for quantified Boolean formulas, QBFs. QBFs are an extension of propositional logic, adding the universal and existential quantifiers. An example of a QBF is shown in the slide. This QBF reads, for all x, there exists a y such that x, if and only if, not y. X and y are Boolean variables. An important thing to note is that if in a QBF there are no free variables, that is, there are no variables which are not bound to a quantifier, then the QBF is known as closed. We only look at closed QBFs in this presentation. Closed QBFs are either true or false. Qsat has many applications, including hardware and software model checking, reasoning, and planning problems, for example, multi-agent planning. In this presentation, for the sake of time, we only will look at two QBFs where the universal quantifier is the outermost quantifier. These are QBFs of the form for all, a set of variables bound by the for all quantifier, there exists, and a set of variables bound by the exist quantifier, and then an encapsulated propositional formula phi. While we only look at this special case in this presentation, our paper looks at the general case, whereby you can have any number of quantifiers in any order followed by a propositional formula phi. Our solver is based off of the Seeger method, which is an iterative method which searches for an assignment to the outermost quantifier's variables, which proves that the formula is either true or false. In our simplified example, that is searching for an assignment to the universal quantifier's variables, which proves that the formula is false. To explain the Seeger method, I'll use the example shown in the slides. So, consider a QBF for all x, there exists a y such that phi. Each iteration, the solver will choose an assignment to x. Let's call it x prime. In the first iteration, x prime will be any assignment, while in future iterations, the choice that the solver can choose x prime will be constrained. To see whether this assignment proves that the formula is false, the solver uses a SAT solver to find the truth value of the formula phi where x is substituted in as x prime. If this SAT solver returns unsat, we know the formula is false. This is because there exists no y which proves that phi is true when we set x to be x prime. Therefore, for all x, there doesn't exist a y such that phi is true. If the SAT solver returns sat, then we do not know yet whether the formula is true or false. In this case, the satisfying assignment returned by the SAT solver to the y's, let's call it y prime, is used in future assignments to help select the assignment to the x prime. This assignment to the y's, y prime, is called a counter move. Let's look at how the Seeger method uses counter moves in more detail. Consider the same QBF as in the slides previously. Scene counter moves are used in future iterations to prevent the solver from selecting assignments x prime for which phi with x substituted in as x prime can be satisfied by one of these previously seen counter moves. This stops the solver from selecting x primes, for which we know will not prove that the formula is false. For example, it stops the solver from selecting the same assignment twice. Using countermoves in this way ensures that for each iteration, you either select an assignment x prime for which phi x substituted in as x prime is unsat, or for one which is countered by a previously unseen counter move. This means that the solver halts only if the solver finds an x prime for which phi substituted with x substituted in as x prime is unsat, and therefore you know the formula is false, or when there are no remaining x primes left which aren't countered by a previously seen counter move. In this case, the formula is true. While the Seeger method achieves good performance, there is a problem with it, in that for many QBFs with simple winning strategies, a Seeger solver will take exponential time to solve it. An example of one of these QBFs is shown in the slide. This QBF can be easily solved by using the strategy of setting each yi to be xi, proving that the QBF is true. A Seeger solver will take exponential time to solve such a QBF, as for each setting of the x's, there is a unique and different countermove. Therefore, to prove that the formula is true, the Seeger solver must see every single assignment to the x's, taking exponential time. In general, when I'm referring to a strategy, I mean a formula of the x's, or a Boolean function of the x's, which chooses a setting of the y's. A good strategy is one which chooses a setting of the y's, which is a countermove to that setting of the x's. To solve one way of solving this problem with Seeger solvers is to use strategies in the solver. Qfun is a method that does this, which uses batch decision tree classifiers to learn strategies. One reason why it uses batch decision tree classifiers is that you must be able to extract the strategy as a propositional formula for them to be used in a Seeger solver. Qfun uses these strategies alongside previously seen counter moves to select in future iterations the assignment to the outermost variables quantifier, the x's in our examples. Let's look at how Qfun uses and learns strategies in more detail. So consider the QBF shown previously 2 slides ago. Qfun, each iteration, stores the seen assignment to the x's and its counter move, the assignment to the y's. This creates a data set from which Qfun learns a strategy, which hopefully predicts from the y's the counter move to it. For the example shown in the slides, a good strategy to learn would be setting each yi to be xi, as this correctly predicts all the counter moves for all the assignments to the x's. Qfun uses strategies just like it uses counter moves, in that using those strategies prevents Qfun from selecting assignments to the x's, the x prime, which we know through the strategy S will not prove that the formula is false. For the example shown in the slides, this means that future assignments to the x's, the x primes, must satisfy the formula in the bottom right-hand corner of this slide. While using strategies improves performance of the Seeger method, it does have a downside in that using strategies can be a double-edged sword. They reduce the number of iterations needed to solve a QBF, but increase the time taken to compute each iteration. Therefore, it is possible to learn bad strategies which increase the time taken to compute iteration more than they reduce the number of iterations needed to solve the QBF. To solve this problem, we present a new solver, IQ, which uses incremental learning to learn only good strategies. Incremental learning allows us to do this because it provides us with low-cost information on how good a strategy is, that is, its predictive performance, and how complex it is. Let's look at how IQ uses strategies in more detail. So, somewhat like Qfun, IQ stores the assignments and the countermoves each iteration. It passes these to its learners, which uses them to update their strategies. IQ uses a strategy only when it's good. That is, it only uses a strategy to select future assignments to the outermost quantifiers variables, the x's, when the predictive performance of a strategy is likely, the predictive of the performance of the strategy indicates that it is likely to boost IQ's performance. In our solver, that means the strategy must correctly predict the countermove sequentially 64 times before it is used. Also, IQ makes sure only simple strategies are used by refreshing ones which are deemed too complex and therefore will only decrease the performance of the solver. To test our solver, we use the datasets from the 2018 and 2019 pre-next non-CNF tracks of the QBF eval competitions. This is the main competition for Qsat solvers. We also, as closely as possible, follow the QBF eval competition's testing setup, whereby each solver has 15 minutes to solve each QBF, and whereby we say a solver fails to solve the QBF if it runs out of time. The solvers tested in our evaluation were R solver, IQ, Qfun, the solver ours is based off of, and QAbs, which is a different type of solver, a search-based solver. QAbs was the winner of the pre-next non-CNF tracks of the 2018 and 2019 QBF eval competitions. This shows it is state-of-the-art. The results we get is that IQ performs better than both solvers for both datasets. This adds evidence to the fact that by using incremental learning, IQ can select and use only good strategies, thereby gaining better performance than Qfun, which does not selectively select strategies and therefore can use bad ones which hurt performance. While overall, IQ performs better than both other solvers for two families of QBFs, the combinational equivalence problems and the bounded synthesis Petri games, QAbs performs better than IQ. This is to be expected, as the particular structure of a family of QBF will be amenable to different types of solving. So, in conclusion, we present a new solver, IQ, which leverages the advantages of incremental learning to learn and use good strategies. This allows it to achieve state-of-the-art performance, performing better in our tests than Qfun, the method it is based off of, and QAbs, a state-of-the-art solver. Finally, one last point to add is that our code is freely available from the link shown at the bottom of this slide. Here are the references I used in this presentation.